Welcome back to the Instranexus. Today, we are diving deep into a critical aspect of industrial engineering that often gets overlooked until it's too late: strategic material certification and integrity assurance. In our industry, paperwork isn't just administrative, it is the backbone of safety. In this video, we will cover the best practices for ensuring the traceability and reliability of the critical materials that make up your industrial systems. Whether you are dealing with instruments, heavy-duty valves, or complex control systems, knowing the provenance of your materials is the only way to guarantee they will perform under pressure. By the end of this session, you will understand exactly which certificates to ask for, when to ask for them, and why they prevent catastrophic failure. Let's get started. First, a quick introduction to who we are. We are Industrial Engineering and Systems. We operate as a professional engineering and systems integration company. Our expertise lies specifically in serving the heavy hitters of the global economy, the industrial sector, oil and gas operations, and power generation facilities. These are industries where good enough doesn't cut it. We understand that in these high-stakes environments, the integrity of a single bolt or a pressure transmitter can determine the safety of an entire facility. That experience drives our approach to material certification. It's not about checking a box, it's about engineering assurance. So, why does material traceability matter? It really comes down to three pillars. First and foremost, it is a safety barrier. Material certificates are effectively the DNA of your asset. They prove that the metal holding back high pressure or toxic chemicals is actually what you paid for. Second, it provides risk mitigation. Proper certification prevents loss of containment and catastrophic failure. If a valve body cracks because it was made of inferior casting, the cost is measured in lives and millions of dollars, not just replacement parts. Finally, there is the legal chain of custody. These documents link the installed components directly to the specific metal melt at the foundry. If an incident occurs, this paper trail is your primary defense to prove due diligence. To manage this, we rely on a specific regulatory landscape. While you will often hear about API, ASME, and NACE, the global heavyweight for certification documents is EN 20204. This standard, titled Metallic Products, Types of Inspection Documents, creates a clear hierarchy of trust. It ranges from the most basic compliance, known as Type 2.1, all the way up to rigorous third-party witnessing, known as Type 3.2. The critical distinction you need to understand is the difference between non-specific and specific inspections. As we move through the next few slides, remember that non-specific means the data is general, while specific means the data comes from the actual hardware you are holding in your hand. This regulatory framework is critical to ensure the safety, reliability, and integrity of industrial assets. Let's look at the bottom of the hierarchy. The EN 10204 Type 2.1, also known as the Declaration of Compliance. This is the most basic level of material traceability. Essentially, the manufacturer is simply declaring, yes, we complied with your order requirements. However, you need to be careful here. These certificates do not include any actual test results or data. There is zero traceability back to a specific material batch or heat number. Because of this, Type 2.1 is typically only suitable for non-critical structural parts, things like brackets, cable trays, or sunshades. If the material properties aren't a major safety concern, this certificate is sufficient, but never accept it for pressure-retaining parts. Moving up a step, we have the EN 10204 Type 2.2, or the test report. Like the 2.1, this declares compliance, but it adds a layer of data. It includes test results. However, there is a catch. The results are from a non-specific inspection. This means the data you see on the paper comes from statistical process control or random sampling of similar products, rather than the specific item being delivered to you. You aren't seeing the chemistry of your bolt. You're seeing the chemistry of a typical bolt from that run. This is suitable for general utility piping, standard fasteners, and non-wetted parts where 100% individual verification isn't economically required. Now we enter the domain of true traceability, the EN 204 Type 3.1 Inspection Certificate. This is the industry standard for pressure-retaining parts in industrial systems. If it holds pressure, you generally need a 3.1. This certificate requires specific inspection results for the delivered lot, including detailed chemical analysis and mechanical testing data. Crucially, the standard requires that these results be validated by a representative who is independent of the manufacturing department. This ensures an unbiased assessment of the material's compliance. When you review a 3.1 certificate, you are looking at the actual DNA of the component you are installing. At the very top of the pyramid is the EN 1204 Type 3.2. This provides the highest level of assurance for critical applications. It requires everything a 3.1 does, but with an added layer of scrutiny: witness testing at the mill or forge, countersigned by an independent third-party inspector, TPI, like Lloyd's or TUV. This rigorous certification process provides the greatest confidence in the integrity and traceability of the material. You will typically see this requirement triggered for use in high-risk, high-pressure, or safety-critical systems where the cost of failure is unacceptable. Let's apply this to real equipment, starting with instrumentation wetted parts. We are talking about diaphragms, flanges, and manifolds. Because these parts form the pressure boundary, a failure here equals a leak. Therefore, a Type 3.1 certificate is mandatory. You need to verify the chemistry, for example, ensuring that 316L stainless steel has a carbon content of less than 0.03%, and verify the physical integrity. Ensuring the integrity of these wetted parts through mandatory 3.1 certification is crucial to prevent leaks and maintain the safety and reliability of your system. What about the rest of the instrument? For housings and electronics, the rules change based on the environment. For standard transmitter housings and terminal blocks, a Type 2.1 or 2.2 is usually the standard. These parts protect the electronics but don't hold process pressure. However, if you are operating in offshore or corrosive environments, the specification must change. In these cases, stainless steel housings require a Type 3.1 certificate to prove they are genuinely 360 Neal grade. Using a lower grade here could lead to corrosion and loss of the instrument. Proper certification here ensures the integrity of the system, even in harsh environments. Moving on to larger equipment, control valves, specifically the pressure boundary. This includes the control valve body and bonnet. As the primary containment for the process fluid, a Type 3.1 minimum certification is required. In high criticality applications, you might even step up to a Type 3.2. Crucially, for castings, the certification must include NDT reports, like radiography or magnetic particle inspection, MPI, alongside the chemical analysis. Robust material certification here is critical to ensure the safety and integrity of the industrial system. Inside the valve, we have the trim and active parts. This includes the stem, ball or plug, and seats. The stem is a critical component. A stem blowout is a major hazard. Therefore, we require a higher level of material certification, Type 3.1, for the stem and the base metal of the seats. However, there is an exception for coatings. Coatings like tungsten or chrome carbide, which are applied for wear resistance, can suffice with a Type 2.1 certification. We need to verify the base metal strictly, but the coating application is treated as a process compliance. A special note on NACE MR0175, the standard for sour service. This is a critical consideration when materials are exposed to hydrogen sulfide, H2S, which causes sulfide stress cracking, SSC. If your project is sour, a standard 3.1 certificate isn't enough. The 3.1 certificate must explicitly list the hardness values of the material. Typically, we are looking for a maximum of 22 HRC, Rockwell hardness. Without this specific data point on the certificate, you cannot verify if the material will survive the corrosive environment. Now let's look at process piping. Type 3.1 is required for all process piping to ensure material traceability. But for piping, the paperwork is only half the battle. You need a rigorous match-up process. The heat number stenciled on the physical pipe must match the heat number printed on the Material Test Certificate (MTC). Strict enforcement of this 3.1 certification and the physical match-up process is the only way to ensure the integrity of your piping network. Similarly, for flanges and fittings, Type 3.1 certification is required. Beyond just chemistry, the focus here is often on the carbon equivalent CE value. We need to verify this value to ensure the weldability of the fittings. If the carbon equivalent is too high, you risk cracking during welding. Also, don't forget instrumentation tubing. Impulse lines require type 3.1 not just for chemistry, but to verify hardness. If the tubing is too hard, the ferrules won't seal properly, leading to leaks. Bolting is often where confusion arises. We must differentiate between pressure boundary bolts and structural bolts. Pressure boundary bolts require a type 3.1 certificate and often need to adhere to API 20E or 20F bolting specification levels. For sour service bolts, like ASTM A193B7M, the certificate must verify 100% hardness testing. However, for simple structural bolts, like those used for mounting a cabinet to a wall, a Type 2.1 certificate is sufficient. Don't over-specify structural bolts, but never under-specify pressure bolts. For control cabinet enclosures, the choice of certification depends entirely on location. For standard industrial enclosures made of painted mild steel, you only need a Type 2.1. But for offshore or coastal applications, we often request Type 3.1 for the stainless steel. Why? Because it is visually impossible to differentiate between 304 and 316 stainless steel without the certification. To prevent your expensive control panel from rusting out in a year, you need that 3.1 paper to prove you received the high-grade 316L material you paid for. What about the brains of the operation? Control system internals, like PLCs and I/O cards. It is important to note that these components do not have EN 10204 material certs. You cannot get a MIL cert for a circuit board. Instead, we rely on product labeling certifications like UL 508A, CE, or ATEX. For traceability, we don't use heat numbers. We use system inventory reports that track serial numbers and firmware versions. This is how we maintain the chain of custody for digital hardware. All of these requirements are useless if nobody checks them. This brings us to the Inspection and Test Plan, ITP. The ITP is the tool we use to define when these certificates are checked. We utilize hold points H, where work cannot proceed without verifying the certifications, for example, at the goods receipt stage for piping. We also use review points R, where the material certification dossier is reviewed, such as during the final inspection of a valve. The goal is to catch issues at the factory, not at the construction site. Finally, we need to address an uncomfortable reality in the global supply chain: fraud. As indicated on this slide, the integrity of your system isn't just threatened by mechanical failure, but by deceit. The risks are substantial. We are seeing an increase in sophisticated counterfeit material test certificates and even physical heat numbers being altered on inferior products to pass them off as high-grade alloy. You must train your team to spot the red flags. Be suspicious of certificates that show generic chemistry values that look like they were copied from a standard rather than tested. Look for missing digital signatures or dates that don't logically align with the manufacturing timeline. To combat this, our strategy focuses on prevention. The industry is moving toward digital MTCs and blockchain traceability to create an immutable record. But you cannot rely on digital trust alone. Implementing positive material identification, PMI spot checks, is your ultimate defense to ensure the metal in the field actually matches the paper on your desk. In summary, strategic material certification is the bedrock of safety and integrity. By adhering to EN 1204 and verifying traceability, we mitigate serious risks. Remember the best practices: Type 3.1 for wetted parts, Type 2.1 for structural, and mandatory hardness data for sour service. Looking ahead, be aware of fraud and digital trends. Risks like counterfeit MTCs and altered heat numbers are real. Watch out for red flags like generic chemistry values or missing signatures. The industry is moving toward digital MTCs and blockchain traceability to combat this. By specifying your requirements explicitly in your requisitions, you ensure that standard documentation doesn't become a safety gap. Thanks for watching, and stay safe. If you enjoyed this video, please like, comment, and share it with a friend. Don't forget to subscribe and hit the bell so you never miss an update.